We are in Unit 10. This is Notes 2. And today we are going to be going over a little bit of a review of what you know about polars. And we're going to be talking a little bit about what we're going to be doing with polars in this unit and in calculus. So first of all, just to kind of refresh yourself on polars, hopefully you did your winter refresher, and so you are already refreshed on this. But this unit, this section in particular, will look at more of the calculus aspects of polar. All right, so first of all, we know a lot about the Cartesian coordinate system, and we can plot points in the Cartesian coordinate system all day long, right? There's point A, -2, -1 is right here for B, and 1, -3 would be right here for C. So we know, and we can graph lines, we can graph curves, we can graph a lot of things in the Cartesian coordinate system. Polar coordinate system is just another system, all right? Instead of being in X and Y, we are in R theta. So whenever you see an ordered pair in polar form, the first coordinate is R, the radius, and the second coordinate is theta, the angle. So if I wanted to graph 3 pi over 3, I go to the angle first. I like doing it that way. So I would go to pi over 3. So pi over 3, remember we start at 0 here, so pi over 3 would go up here, so there's pi over 3. And then R is 3 here, so pi over 3, we start at the origin and we go out 3 units. 1, 2, 3. So this would be point B. A, the origin, is called the pole in coordinate and polars. However, we'll still call it the origin as well. So both mean the same thing. Okay, 5 pi over 6. Go to 5 pi over 6. It's right here. And then you go out 4 from the origin. So 1, 2, 3, 4. And there's point C. 7 pi over 6, 2. Well, here's 7 pi over 6. Remember, you start at think of it as starting at 0 and going around to 7 pi over 6, and then you go out 2 units and you're there. Okay, 7 pi over 4 would be starting at 0, go all the way around to 7 pi over 4, and then you go out 1 unit from the origin or the pole. So this was D and this is E. All right, since theta can be negative, R can be negative as well. Since theta can be negative, we can keep going around the circle again and again. Every point can be written in an infinite number of ways. So this point B, let's see if I can sharpen that up a hair. This point B, which is 3 pi over 3, is also 7 pi over 3. So think of it starting at 0, going all the way around to 6 pi over 3, and then going another pi over 3. That would be 7 pi over 3. Or 3, and then negative 5 pi over 3. You're still starting at the origin, but instead of going counterclockwise, if theta is negative, you're going to go clockwise. And you're going to go clockwise 5 pi over 3 units, which would take it all the way around to here. Okay, etc. R can also be negative. So if I wanted to plot this point, I would first go to this angle, 4 pi over 3. View right here. There's 4 pi over 3. And then I need to go a -3. So along this line, I need to go -3, so it's back through the pole on the other side. So point B is also this point as well. Okay? So every point in polar has an infinite number of ways to name it, unlike Cartesian. 2, 3, that's the only point. This will never be named anything else in Cartesian coordinate system. All right. If we lay the Cartesian coordinate system on top of the polar system, we can write the same point in either rectangular form or polar form. So this point, I could name it in xy's or I could name it in r thetas. Alright, so we need a way to switch back and forth. So if you draw a little triangle here and name this theta, we know that this point would be xy, so this distance here is y, this distance here is x. This distance is the radius, so it's r, right? So cosine of theta is adjacent over hypotenuse, so cosine of theta is x over r. And if we multiply by r on both sides, we get x is equal to r cosine theta. Sine of theta is y over r, so y is r sine theta. Tangent theta is opposite over adjacent, y over x, so theta, I could say, is arctan of y over x. The Pythagorean theorem holds, so r squared is equal to x squared plus y squared, which gives me a way to get r by itself. So these are the things that you need to know. All of these. And I don't memorize them, I just know where they come from. And after I use them a bit each year, it's always in my brain. Okay? X has cosine. Y has sine. Alright? Now, the absolute value of r is the distance from the origin to a point. Because remember, r can be negative. Alright? So if you want the distance from the origin to a point, it'll be the absolute value of r. Okay? I know that seems easy. But it's also easy to forget when you're working on a FRQ. Alright? Particularly when you're trying to find the maximum distance, don't forget about those negative r values. Alright? You want the absolute value of r, not just a plain r. Alright. Next up. Next page here. Graphing polar equations. Alright, so, and I'm going to let you read all this. For the AP exam, you don't have to know the graphs of any polar equations. However, if you do know some of these basic graphs, you will be able to save yourself some time because you won't have to think about how to graph them yourself without, if you know what the graphs of these look like, then you'll be able to answer the problems that you're being asked without taking the time to actually graph them. Okay? What you do need to be able to do is to find the theta values needed to form a complete graph. And this, if you know the graphs of these, it's helpful to be able to do that. Find the theta values needed to form part of a polar graph. Find the intersection points of two polar graphs. So those are crucial in this section. We need to do these three things in order to find the area inside of a polar graph or part of a polar graph. Right? All right. I'd like to show you we're going to walk through this. So grab your calculator and let's put it in polar mode because we are going to be looking at graphs. So let's get it in polar mode. I still have our last section in here. I'm going to get rid of all these things. So go to mode and let's go into polar mode, which is down here. Keep it in radian mode. We always stay in radian mode in calculus. Okay? All right. Now, we're going to sketch using a bubble. I'll show you how to do that so you can actually see the curve being sketched. I will tell you that I have kind of an older TI-84 calculator here. Some of the newer ones, you're not going to be able to see it being graphed. The graph just pops in there. I kind of like, especially for this, it's helpful to see the graph as it goes around, as it goes from 0 to 2 pi or whatever our theta values are. Okay? All right. And again, you can read that as we go. All right, for each of the following, find the values of theta needed to form a complete graph, then sketch the graph. Okay, so let's go to our, if you push, when we're in polar mode, if you push y equals, you don't get y equals, you get r equals. Okay, so I want, well, let's put in 3 plus 2 sine theta. Okay, now, this is one of our known, I would like you to be able to recognize these. This is one of our known graphs, okay? For our known graphs, we are either going to be going from 0 to 2 pi or 0 to pi. What I'd like to do is always start off by going 0 to 2 pi, and we'll see if that's enough. Now, this step value, theta step. The higher this is, the more jerky, the fewer points are that are going to be graphed. The graph will be more jerky. The smaller it is, the nicer your graph will look, but the slower it will take to graph. So you don't want to make this too small, because then you're going to be sitting here for an hour watching this graph make, and you don't want to do that. All right. For the x's and the y's, I'm just going to zoom for that. So I'm just going to zoom for, now we have that. So does that look like the complete graph? No, it does not look like the complete graph because we're missing a part up here. Okay, so what I'm going to do is do zoom, and then I'm going to do zoom out. So 3, enter. It zoomed way out, but we get the idea of what's going on there. Okay, now I'm going to zoom back in because I like that one better. Okay, so I know what's going on. So when we graph this, and by the way, it does look like that formed a complete graph. If we go to our window and change it just to pi, going 0 to pi, let's see if that formed a complete graph. It did not. It went from 0 to pi. For this graph, we need to go from 0 to 2 pi, right? So I'm going to change it back to 2 pi. Okay, now I told you that I was going to show you how to do this bubble, so let me show you how to do this bubble. Here I can totally see it going, but go to your y equals, and if you go to your equals, actually go all the way over here. Go past the r, like that, and then push enter. That makes the line darker. That's one way to distinguish between two graphs. You enter again, and do you see the little bubble? That's what you want. And now when you graph it, do you see the little bubble there? It just allows you to follow your graph a little bit. Okay? It's especially helpful if you have accidentally put in too many theta values. Because what if we went, instead of to 2 pi, what if we went to 3 pi? Then we're going to get more theta values than we want, right? It's going all the way around to 2 pi, slowly. And then it's going to keep on going. And it's tracing the same graph again, right? So that's why I like the bubble there, because I can see what's going on. If I didn't have the bubble there, I wouldn't be able to tell that it was still even going, right? So this graph, this is a lemmasome with no loop. It's a lemmasome with no loop. Now, I would like you to know what the graph of this looks like without getting out your calculator, because this could be on a no calculator part. And if you didn't have a calculator and you needed to know these things, you would have to start plotting points, and that's not fun. First of all, it's in the form of a lemmasome, okay, because there's a number plus or minus, a number sine or cosine theta. It has to be a 1 theta in here to be a lemmasome, okay? To graph it, here's what I think. I see a 3 and a 2 here, a 3 and a 2 here. Well, first thing I do, I see the positive sign. Do you see the positive sign? Positive sign tells me the bulk of this is above it's on the positive y-axis. Remember, sine and y go together. So this is up on the positive y-axis, the bulk of it is, because it's positive y-axis, all right? How far up? 3 plus 2. That's how far up. 1, 2, 3, 4, 5. That's how far up you go. It's a limacon. You go side to side this many. Always. Side to side that many. Now, the next question is, it is a limacon, but some limacons have a little loop and some limacons do not have a little loop. How can you tell? Here's how I tell. This 3 is bigger than the 2, right? 3 is bigger than the 2. If this number is littler than this number, then your limacon has a little loop. If this number is bigger than this number, then your limacon does not have a little loop. It pokes out the other side of the origin. Okay, how far out does it poke out? Subtract these two absolute values. 1. That's how far out the other side it goes. And then when you draw your curve, you should draw your curve nice and plump. Nice and plump. Okay? Complete graph. Zero to 2 pi. That's what we need for a complete graph. If we start at 0. If we started at pi, then we would need pi to 3 pi, right? It's just common to start at 0. 0 is a nice number for us. All right? Next up, let's see if we can do this without getting on our calculator. Okay? Without getting on your calculator, recognize that this is a limacon. Okay? This limacon sits on the negative x-axis. The bulk of it sits on the negative x-axis. How far out? 6. 6 units out. 1, 2, 3, 4, 5, 6. 6 units out. How far side to side do we go? 2. Does it have a little loop? The 2 is littler than 4, so it has a little loop. How big is the little loop? Subtract these two absolute values. The little loop has length 2. If your limacon has a little loop, then yes, it goes to the origin, and then you go to your loop. Okay? So this limacon, make it nice and plump. No skinny, wimpy limacons, okay? Make it nice and plump. Something like that. And you can confirm it on your calculator. Okay? If it's a limacon, all limacons need a complete graph of 0 to 2 pi. So 0 to 2 pi. If it's a limacon, 0 to 2 pi. Alright, next up. This is not a limacon. It's something else. So if you want to play on your calculator and go find it on your calculator, go for it. I'm going to show you how I would do it because we don't need a calculator for this one. This is not a limacon. I see a number here. This is a rose. Okay, it's a rose. And each petal of the rose has length 4 units. Each petal does. It's a cosine, so I know that the first petal is going to lie on the x-axis. It's a positive cosine, so I know that the first petal is going to lie on the positive x-axis. So I'm going to draw a petal because I know it's there. And it has length 4. Now this number is 3. That tells me if this, remember, if that's odd, then we have that many petals. If it's odd. If it's even, like it will be over here, then you have twice that number of petals. This one has 3 petals, so we're going to distribute those petals evenly around the system, the coordinate system. Each petal has length 4. Okay? So if you confirm that on your calculator, 4 cosine 3 theta, there it is. Okay? Now, did you see what was happening there? Let me turn back on my bubble. I like to see how it's graphed. It's interesting. Look what's going on. It's tracing it again, isn't it? It's going over the same graph again. What was my window? It's going over it even again. How many times is it going to go over it? Okay, stop. What was my window? I was going to 3 pi. I believe it went over it 3 times, so I think I only need 1 pi there. See if it makes it all the way around. It did, and it stopped. You want to know what theta values form a complete graph. So this needs only from 0 to pi. That needed only from 0 to pi. Let's go to this one. So for this rose, and it's in the form of a rose because they've got a number and then sine or cosine, and then your theta. All right. For this rose, I see a positive sign, right? A positive sign. Now, for sine and roses, it's a little bit trickier to figure out where it begins. Unlike with cosine, I can stick that either on the positive x-axis. If it was negative, I'd stick it on the negative x-axis. That one's really obvious to me. This one, you have to know a bit about these. Okay, but for sine and even petals, no petal sits on any axis. No petal sits on any axis. So here we're going to have 4 petals because that number is even. Each petal is of length 3. So this is going to look something like this. Kind of like a butterfly, where each petal is of length 3. Okay? Let's go check it out. So 3 sine 2 theta, and it's still on bubble, so that's good. My window is still 0 to pi. Do we think it'll be 0 to pi? Well, let's find out. There's my first petal. It stopped. I only got half my butterfly, or rose. So I think I need to double that. We'll see if we get it all this time. I think we're going to get it all. Okay. All right. Notice that there is some error in this graphing calculator. It doesn't show all these petals going to the origin. We have to know that they are going there, though. Sometimes you have to interpret these correctly. So this one needed 0 to 2 pi. Okay. Excuse me. So that was kind of interesting. Both roses, odd numbered petals only need 0 to pi. Even numbered petals need 0 to 2 pi. Okay. All right. Next up. This looks more like a limacon, doesn't it? It looks like a limacon in a form, but the two numbers are, the absolute value of those two numbers are the same. This is called a cardioid. So this is a cardioid, but we graph it the same way that we did a limacon. It's just that there's no loop and it doesn't bump out, it just goes through the pole. So I see positive y-axis. That's where the bulk lies. Go out, how far? 2 plus 2, 4. Side to side, 2. The absolute values are the same, so no loop, no bump out, it just goes through the pole, and that's all there is to it. Okay? That's it. So what do you think this needs? It's so much like a limacon. This will also need the 0 to 2 pi. So this one also needs 0 to 2 pi. Okay? What about this one? This one looks more like a rose. It's in that form, right? This one looks more like a rose, and we treat it like a rose. Okay? I see a negative cosine, so I know the bulk, this is going to lie on the negative x-axis. Okay? Now, how many petals will there be? What is that theta coefficient? 1 petal. That means it's a circle. 1 petal means it's a circle. This is a circle. The circle is going to have diameter, or petal length, 4. So 1, 2, 3, 4, and this is going to be a nice plump petal circle. Okay? So that's just a circle, but you can think of it as a 1-petaled rose. If you think of it as a 1-petaled rose, then what theta values do we need? 0 to what? Well, if it's a 1-petaled rose, that means it's an odd-petaled rose, so it only needs 0 to pi. And you can test that on your calculator to confirm that. Okay, so here's what we found out. Odd-petaled roses, 0 to pi. All other circles, roses, cardioids, limacons, 0 to 2 pi. Odd-petaled roses, 0 to pi. That's what I want you to know. Okay? All right. The absolute value of r, remember, is the distance from the origin to a point on the curve. We can find the theta values when our curve is at the origin by setting r equal to 0. Let me say that again. If we want to know the theta where our curve is right here at the origin, when it's right here at the origin, that means that r is 0, right? So if we wanted to find theta, we would just take r and make it 0. So I'm going to take r and set it equal to 0, and that will give me the theta values right when the curve is at the origin. Okay? So this is going to give me cosine theta is -1. And what value of theta between 0 and 2 pi makes cosine of theta -1? Well, there's only one, and it's pi. So the only value of theta it only goes through once, so there should only be one answer here, right? Unless we started there. Okay? All right. Over here, let's do the same thing. How many answers should we get here? How many times does this go through the origin? It looks like 6 times to me. This is not one of our known graphs. Okay? All right, let's find out. Let's take our equation for r and set it equal to 0 to find where r is 0. So if I subtract 3 and then divide by -6, I'm going to get sine of 3 theta is positive 1/2. Okay, how do we solve that? I'm asking you to think back to pre-cal. Well, to solve that, 3 theta must be the angle that makes sine 1/2. So pi over 6, 5 pi over 6. When I used to teach pre-cal, this is what I would say. I would say, okay, it's a 3 theta, so keep going around the unit circle and grab two more sets. So you want 3 sets total. Okay, so pi over 6, if you add 12 pi over 6, you get 13 pi over 6. 5 pi over 6, if you add 12 pi over 6, you get 17 pi over 6. 13 pi plus 12 pi over 6 is 25 pi over 6. And lastly, 17 pi plus 12 pi over 6 is 29 pi over 6. Now, multiply both sides by 1/3. And then you'll have theta by itself, right? So theta will be pi over 18, 5 pi over 18, 13 pi over 18, 17 pi over 18, 25 pi over 18, and 29 pi over 18. Those are our answers, all 6 of them, okay? That's how I would solve that. Next up, it's a weird little graph. Okay, let's find out when r is 0. So I'm going to take r and set it equal to 0. Well, I don't really want to subtract that over and divide by theta because I'm going to be losing something if I do that, right? So instead of subtracting it over and dividing by theta, I'm going to just factor that theta out. If I factor that theta out, things get nice. Then I get either theta is 0 or 1 plus cosine theta is 0. Well, theta is 0, that kind of makes sense because if I put 0 in for theta, I get 0 for r. So that means when theta is 0, we're starting at the origin. Okay? Over here, I get cosine of theta is -1, and in between 0 and 2 pi, that means theta is pi. So I started at the origin, and then I went all the way to pi, and I'm back at the origin. Or maybe it goes like this. No, it goes like this. And then it goes around. So my two theta values are 0 and pi. That's where r is at the origin. Okay? If you want to see more of it beyond 0 to 2 pi, you could grab that on your calculator and see. Okay? I'm thinking there's 1, 2, 3, 4, maybe 5 here. Maybe 5 here. 5 times this graph goes to the origin, because I think it starts there. If we put 0 in for theta, what is sine of 0? 0. So we're going to start right here at the origin. Okay, let's set this equal to 0. Divide both sides by 4. So we'll have 2 theta is equal to. Okay, what angles make sine 0? 0, pi, 2 pi. But we have a 2 theta, so let's do it again, right? Pi plus 2 pi is 3 pi. right? 2 pi plus pi is 4 pi. And I think that will do it for us. I think that will be all we need to make it between 0 and 2 pi. So divide both sides by 2 or multiply both sides by a half. And we have all of the values of theta between 0 and 2 pi that make r 0. Okay? Next up, what about this one? 2 plus 4 cosine of 2 theta is equal to 0. It looks to me like, it looks to me, if I put 0 in for theta here, cosine of 0 is 1, isn't it? So we're beginning right out here. That's when theta is 0. So I'm thinking 1, 2, maybe 1, 2, 3, 4. I think we're going to have 4 answers here. So cosine of 2 theta would be a negative 1/2 when you subtract the 2 and then divide by 4. So 2 theta would be, I need the angle that makes cosine negative 1/2. So that would be 2 pi over 3, 4 pi over 3, and then I need one more set. So add 6 pi over 3, 8 pi over 3, add 6 pi over 3, 10 pi over 3. And now take half of both sides. Half of both sides, this will be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. All the pi over 3's. Okay? All right. Last one in this little section. For this is graphed only between 0 and 3 pi over 2. Okay? If we put 0 in for if we put 0 in for theta, what's our first point? 0. So we're starting right at the origin. So it looks to me like, I'm not sure if the little loop is formed first or the big loop is formed first. It looks to me more like this little loop is formed first, and then it goes out like that. So I'm thinking we start at 0. I don't know what theta is here, but we get back one more time, and then we go around and we're back again. So I'm thinking we're going to have 3 answers here. Let's find out. 2 theta cosine theta is equal to 0. So that means either theta is 0 or cosine theta is 0. What values of theta make cosine 0? Pi over 2, 3 pi over 2. So there are our answers, all 3 of them. So I wanted to show you some graphs that were not some of the known ones that you just would know. And I wouldn't know what these look like without graphing it. Okay? All right. For these, we're going to be doing the same thing, but we're going to need a calculator, as you'll see. So when we set, on this one, when we set r equal to 0, we get sine of theta is negative 2 over 3. Do we know an angle that makes sine negative 2/3? No, we do not. Okay? All right, here's what I'd like you to do. I want you to go back to function mode. Since we're doing a calculation, I want you to go to function mode. All right? Function mode. And go to y equals. And I'm going to put in, well, we can put in either one. 2 plus 3 sine theta will work. Sine x. And I'm going to put 0 for my other equation. And then we're going to see where these two intersect. Okay. I only want between 0 and 2 pi. So please go and restrict your window from 0 to 2 pi. Why see more than you want to see? I don't know. Okay, there are our 2 theta values right there. So second calc 5 for intersection. Enter, enter, enter. And this will give us our first theta value. Okay, our second theta value. is 5.553. Okay? That's how I would do that one. Yes, you can do it arc. Here I could do arc sine. If you did arc sine here, I did arc sine, so second arc sine of negative 2/3. What's it going to give me? It's going to give me a value. That's a theta value. It's just not in the range that I want it to be in. It's not in my domain. So then you'd have to mess with that. You'd have to mess with it to get these two values. Why do that to yourself? Why not just go and find them on the graph? Okay, that's my thought on that. But if you really want to mess with those, go for it. Okay, so for this one, let's just set this equal to 0. So 3 minus 5 cosine theta is equal to 0. Let's do the same thing. So I've got 3 minus 5 cosine x, and I still have it 0 to 2 pi, so I'm just going to graph that, see what happens. I'm not seeing everything up there, but I really don't have to see everything up there because my two theta values I'm looking for are right here. So second calc 5, I'm going to scooch over here a little bit, enter, enter, enter. There's my first theta intersection point. Okay, and then go grab your other one. Enter, enter, enter. And there's my second one, 5.356. So with a calculator, these are easy to find. Okay, to find, now we're going to find where two equations intersect. So we're trying to find the theta values where two equations intersect. Okay, so we're trying to find this theta value and this theta value. I like to draw my theta lines. You'll see why when we're doing the areas and stuff tomorrow, but I like to draw those theta lines. Okay, so we're setting 3 sine theta equal to 2 minus sine theta, and we're seeing where they intersect. So if I add sine theta to each side and then divide by 4, I see that theta is pi over 6 and 5 pi over 6. And doesn't it look like 5 pi over 6? I'm sorry, pi over 6 and 5 pi over 6. So this is pi over 6 and that's 5 pi over 6. So visually it confirms. Okay, over here we have a lot more intersection values, right? Over here we have 4 sine, well we have lots of intersection values. Do you agree? Okay, 4 sine of 2 theta, and we're setting that equal to the other r, which in this case is just 2. So sine of 2 theta is a half. So 2 theta is pi over 6, 5 pi over 6, right? Okay. One thing about this one. Well, I'm going to continue. If we add 12 pi over 6 again, we get 13 pi over 6, and we get 17 pi over 6. This is only going to give me 4 answers, and I know I've got 8. What's going on here? What's going on here? Well, here's what's going on here. This r is equal to 2. R is equal to 2 is giving me this, but r is equal to 2 is the same thing as r is equal to negative 2. Do you agree? Same thing. So this, I would actually need to make this plus or minus there. Plus or minus here if I want all 8 intersection points. So yes, these are 4 of them, but now I need to go get those other 2 quadrants. So I'm going to add to this 7 pi over 6 and 11 pi over 6, and I'm going to add 12 pi over 6 to each of these. So 19 pi over 6 and 23 pi over 6. And now divide everything by 2. And I'm going to let you finish that. That's what you would do to get all 8 of those values. Okay? For this one, for number 17, let's find those 2 theta values. See what those are. So we have 4 plus 2 cosine theta is equal to 3 minus 2 cosine theta. Okay? So I'm going to add 2 cosine theta, and I'm going to subtract the 4. Then I have cosine theta is negative 1/4. I don't know that one offhand. That's not one of our unit circle values, is it? So this is one that we have to have a calculator to do. So I'm going to come and do the same thing that we did before. So I think since I already have this in here, I think what I'm going to do is I'm just going to do this here, 4 cosine x plus 1. And that way I'm pulling that over to this side, right? And I want it to be between 0 and 2 pi, so that should give it to me. There are my 2 theta intersections. Second calc 5. Enter, enter, enter. 1.823 and 4.460 if I round that. Okay. All right. So this is just just reviewing just things that you can do with these. All right. Now another thing that we have to be able to do is we have to be able to change things from polar to rectangular and from rectangular to polar. So let's get a little practice here. If we have this equation and we want to change it to rectangular, they're giving us what the answer is, we just need to get there, okay? So what would I do here? I would probably begin by multiplying both sides by this denominator. If I did that, I would get r plus r sine theta is equal to 4. I would get that, right? And I like that because all of a sudden I've got y, and that's a good thing. I like having y. And I know what r is. R is the square root of x squared plus y squared. So what I have now is the square root of x squared plus y squared plus y is equal to 4. Okay? I need to do something to that to get it to look like this. So I'm going to isolate my square root. And now I'm going to square both sides. So I'll have x squared plus y squared. And now I square this binomial. Don't get lazy. 16 minus 8y plus y squared. The y squareds are going to cancel out, right? So I'll have x squared is 16 minus 8y. We're almost there. I'm going to move the 8y over. And I'm going to move the x squared over. And now I've done it. QED. I've shown it. For number 19, we're starting out with this equation. What a mess. And we're going to show that it's equal to that. Okay, so I'm going to begin by getting rid of the square root. There's no square root here, there is here. I'm going to get rid of the square root. So I'm going to have y squared, square both sides. So already looking good. now I'd like to get rid of this fraction. So I'm going to multiply both sides by 4. Multiply both sides by 4. Looking better. Okay, looking better. Okay, now what? Now what? So think about what we can do. Here's what we have to go by. I see that x squared and y squared. I'm like, that's looking kind of nice. So I'm going to move my x squared over on that side. And now I'm going to substitute in place of y. In place of y, I'm going to put r sine theta. In place of x, I'm going to put r cosine theta. Let's see what happens. Oops, cosine theta. Alright. So I have 4r squared sine squared theta plus r squared cosine squared theta is equal to 4. I'm looking at what I have to get to. I'm going to factor out an r squared. And I'm almost there. Just divide by what's within r squared. So a little manipulation here, guys. Alright, we are ready to begin applying calculus to this. We're going to be looking at area. We're going to be looking at tangent lines tomorrow.